So last time we learned about decimal fractions. Now I want to talk about recurring decimals or recurring decimal fractions. So these are fractions whose decimal expansion repeats indefinitely. So let me try to explain what I mean. So let's think of a fraction like 1 over 3. So if I have a fraction like 1 over 3, um, there's no way I want to write it as, I want to convert it into some power of 10. So I would like to write it as 10 raised to the some power. And the question is, can I do that? And if you think about it, there's no way that you'll be able to do it. So here's something for you to um, mull over, that the question really is, I want you to think about it, why can't you do this? So why can't you do this? So this does not work. So if you try to convert 3, because remember we had an eighth last time, and when we had an eighth, by multiplying by 125, we got it to 1,000. So we could get the denominator in a decimal form, like a power of 10, and then we could write our decimal fraction easily. But if you try to write 1 over 3 as, and you want to convert 3, the denominator, into some power of 10, like 10 or 100 or 1,000 or 10,000 or 100,000, you just can't do it. It's impossible to do. And I want you to think about, why can't you do it? So this is one question that I want you to think about. So this is one important question. So this is question number one. Why can't you convert a 3 into some power of 10? Please also note that numbers like, if you think about it, 2 over 7 and maybe 4 over 21, and maybe numbers like other such numbers cannot be um, converted into powers of 10. So there must be a reason why they can't be converted into powers of 10, and I want you to model it. Anyway, so we can't use the first method that we had to convert 1 over 3 into a decimal fraction. Let's try to use our regular division method, and maybe we can convert that into a power of 10. So 1 over 3 is really 1 divided by 3. So I can divide 1 by 3. So I can certainly divide 1 by 3. So I can't give 1 to, if I have one thing, I can't give it to 3 children. So I can give 0 units to each child, and I can think of 1 as 10 tenths. And I can certainly give 3 tenths to 3 children each, and I'll have given away 9 tenths to the children, and now I'll be left with 1 tenth. I can't give 1 tenth away, so I can think of 1 tenth as 10 hundredths. And then I can again give 3 hundredths to the children, and I'll be left with 1 hundredth. I can't give 1 hundredth away, so I can think of 1 hundredth as 10 thousandths, and then I can give 3 thousandths away, and this will continue, dot dot dot, right? So what that means is that what we've just discovered is that 1 over 3 is equal to 0 point, and this is a weird thing that we are doing. This is 0.3333333. It never seems to stop. This is the first number that we have written down as a decimal number whose decimal expansion doesn't seem to stop. Okay, such decimals whose decimal expansion does not stop and actually patterns repeat. So here's a pattern that is repeating, the 3 is just repeating, are called recurring decimals. And the notation that we use, so this is the notation that we're going to use. So we're going to write this as 0.3, but with a dot on top. And the dot on top means that 3 is going to repeat itself over and over again. So let's look at another example. Let's look at an example like 1 over 6. So I want 1 over 6. And again, there's no way that you can write 1 over 6. If you want to write it as a decimal fraction with some power of 10 in the denominator, you can't do it. And you should have you should think about why you can't do so. So let's use the other method, which is the division method. So it's a division interpretation of fractions. So now I'm just going to do this quickly. This is going to be 4 tenths and then 40 hundredths. So I'm going to get 6. I'm going to get 36, and I'm going to get 4, and again I'm going to get another 40. So sorry, so I should have written it slightly better. Maybe I should write the 6 right over. So this is a 1, this is a 6. So now I'm going to get 36. So now I'm going to get 36 again, and this will continue, and this will continue, dot dot dot. Okay, so you can see that 4 is repeating itself again and again, and this will never stop. So I can write 1 over 6 is equal to 0.1666 dot dot dot, and the way we write this dot 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 is we're going to put a dot on top of the 6. So the dot on top of the 6 means that 6 is going to repeat itself. So let's try another one. Let's try another one and look at 2 over 7. So if you look at 2 over 7, well, again, there's no way to write it up. So let me just divide 2 by 7 is just equal to 2 divided by 7. So I'm just going to divide 2 by 7 and see what I get. So let's start. Sorry, not 3, but 2 7s are 14. 6, this is going to be long. 8 7s are 56. 5 7s are 35. 7 7s are 49. 1 7 is 7. 4 7s are 28, and now I get a 2. Now please note, this is interesting to note. So this is where the pain now stops. Because note there was a 2 here, now I get a 2 here, right? So now note what's going to happen. I'm going to pull down a 0, and I'm going to get a 20. So now this is the same 20. This 20 right over here is the same 20 that I have over here. So that means the pattern will start repeating. So now I'll again go 2 7s are 14. So this 2 right over here, will be the same as this 2 right over here, because I'll again go 2 7s are 14, then I'm going to write 14 down, and this will continue right over here. So if I write down the 14, so this 14 is exactly the same as the 14 above, and the pattern will now repeat itself. The whole calculation will start to repeat itself. So now what you find out is that 2 over 7, so I write it down here. So 2 over 7 can be written as a decimal expansion, which is 0.285714, and then I have 285714 dot 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 dot. So you can see that this 285714 is going to repeat itself. So what you do is you write down this as 0.285714, and you put dots on 2 and dots on 4. So what that means is that this pattern starting from 2 and ending at 4 will repeat itself. So here's another question for you. So hopefully at least this calculation should be clear. The question is, why are you guaranteed that for any fraction, the pattern will repeat. So the question is, why for every fraction? So if you have any fraction of the form a over b, you will get a pattern that repeats. So you get a recurring decimal expansion. So maybe I should just say you get a, so the question is, why do you get a recurring? So the question is, why is this true? So why are you guaranteed that when you have a fraction, you will get a recurring pattern either with dots or it will be finite? So you could have something like what you had earlier, which we did last time, or it will be of the form something like this, which is something that repeats. So I want you to think about these two questions. The first question was, why is it that certain fractions cannot be converted into powers of 10? Their denominators cannot be converted into powers of 10. And the second question is, why are you guaranteed that whenever you have a fraction, you'll always get a recurring expansion? And if you will, you can think about a simple decimal fraction like maybe 1 over 4 as 0.25, but 0.25 is really, you can put in as many zeros as you want. So this pattern is really repeating itself, right? So this zeros, which are redundant, are really the recurring part. So every fraction can be thought of as a recurring fraction, although in our terminology, we call recurring fractions those fractions which do not end with a zero. These are called terminating fractions. So these fractions we call terminating, but you can think of them as a weird kind of a recurring fraction, but these are called terminating fractions. Okay, so that just to be clear about the terminology. So I'll see you next time.